One of the key properties of any wave is the wave speed. The speed of transverse wave on a string is determined by the tension in the string. Let's call it force of tension, and the mass per unit length, known as linear mass density, which equals mass per unit length. So when you increase the force of tension, it also increases the restoring forces, which tends to straighten the string when it is disturbed. That leads to increase the wave speed. When you're increasing the linear mass density, it makes the motion more sluggish and so decreases the wave speed. Let's consider a small piece of string that has been displaced from equilibrium by passing a wave. To do that, let's focus on a small tiny segment of this string between point x initial and x final, and the segment has a length of delta x. Let's see. Let's try to attempt to write the equation of the motion for that segment. For that, let's see what forces act on that segment. The segment is subject of two forces, one from each adjacent pieces. So if I draw this, one force will be here, force of tension, and then the other one here. So both adjacent sides pull this little segment. The ends of this element make small angles, theta initial and theta final. So to show that, I am going to make a horizontal line. So this would be my horizontal line. This angle here would be theta final, and here the angle here would be theta initial. Now, since this is a very tiny element, we can treat it as a point and draw a free body diagram. You might want to ask, why am I drawing a free body diagram? Here is my strategy. I'm thinking if there is a force, then the force is the one that causes the acceleration, the speed. So, since I have the forces and I want to find the motion, then Newton's second law will be very, very helpful. So my plan is to apply Newton's second law. So I'm thinking of, if I write sum of the forces on the x equals max, and sum of the forces by y equals may. So let's see. We know that when the wave passes through the string only moves up and down. Each segment, each element of the string goes up and down, but it doesn't go on the x-axis. Therefore, the acceleration on the x-axis is 0, and we're actually not interested in this. We're interested in the motion on a y direction because that's a transverse wave. So therefore, I'm going to focus on some of the forces on y. So for that, I need a free body diagram. So let's draw a free body diagram. I'm going to choose my x and y coordinates. Here's my x, here's my y, and this would be my little element string. And let's draw the forces. So here's the forces on the left end, force on the left end, and this is the force on the right end. Let's put the vector signs, not forget about it. And these angles right here, I have theta final here, and I have this one to be theta initial. Okay, so then let's resolve this into components. So Here we have fx component on the right side, so that be f cosine theta final. On the y-axis, we would have f sine theta final. Same thing let's do for the left side. So f, we have a sine theta initial, and here we have f cosine theta initial. Now let's find sum of the forces by y, which equals f sine theta final minus f sine theta initial. And let's factor the f out. That's f sine theta final minus sine theta initial. Well, you might want to think like, okay, now we got a theta initial, theta final, how we're going to deal with that. Well, let's see, what can we do? We know that theta initial and theta final are very small angles. So therefore, I can make this approximation sine theta approximately equals tangent theta, and I can rewrite sum of the forces by y approximately equals force times tangent theta final minus tangent theta initial. But we know also that this tangent theta equals dy dx. Okay, so since we are looking at the angle at a particular instant, like time is constant, right? Particular at a particular instant. Then this would be approximately, I mean, we can write this as a dy dx as a partial derivative. Now I can substitute the tangent theta with dy dx into the above equation. Let's make more space in here. So then I would have sum of the forces by y equals force times, okay, here what I have, dy dx final minus dy dx initial. Okay, now we can apply the Newton's second law. Okay, rewriting Newton's second law, sum of the forces by y equals may, and let's recall from if we have the linear mass density, m would be equal mu times the length delta x. Okay, so and the ay here would be equal d to the second derivative of y by t. Okay, now let's substitute everything. For sum of the forces by y, I'm gonna write force times dy dx final minus dy dx initial equals mu delta x d2y dt2. I hope you're already seeing something similar happening to our wave function, a wave equation, but on the right side you can see d2y dt2. So let's see how can we make it happen. So if I divide both sides by delta x, So then take the limit when delta x is going to 0 on the left side. So let me do a side work here. Let's recall what is a derivative, definition of derivative of any function. Let me choose a different color because it's a kind of a side work we're doing. So let's see, df f dx, it's a definition, equals limit when delta x goes to 0, f of x plus delta x minus f of x divided by delta x. So we can associate fx plus delta x with dy dx final, and fx fx we can associate with dy dx initial. Then if you take a look at this equation, when you take a derivative on the left side, we would have this whole thing with the limit I can rewrite as d dx of dy dx. Okay, so remember my f of x is a dy dx is associated with that. Okay, and then so I had a f in here that equals mu times d2y dt2. Now let's move on. So this expression here, I can write d2y over d dx2 equals, I can write mu over f d2y dt2. Now let's recall what was the wave equation. So our wave equation has this form, d2y dt dx2 equals 1 over v squared d2y dt squared, or 2. So if you compare these two equations that we got, we can simply say that mu over f equals 1 over v squared. From here follows that v squared equals f over mu, or v equals square root of force over mass density. It turns out that for many types of mechanical waves, not only the string, the wave speed in general equals square root of restoring force that returns the system into the equilibrium over the inertia resisting the return to the equilibrium. So I'm going to write this in here. Inertia resisting the return to equilibrium. Maybe I should add restoring force that restoring force returning the system to equilibrium. Okay, so the speed equals restoring force, square root of restoring force, returning the system into the equilibrium over the inertia that is resisting the return to equilibrium. So in our case, with the string, our mu provides the inertia.